Okay, so for this assignment, I am doing a repeated measures ANOVA. So the first things that I kind of want to do is talk about what a repeated measures design is. So it's a specifically experimental design where you use all the same people and they participate in each conditions of the experiments at different points in time. So for this specific assignment, we're doing a one-way repeated measures ANOVA. So not this means, there we go, that's better. So the predicted variable, yeah. The predicted variable are categorical in nature with 3 or more levels. The outcome variable is continuous. You really want to use this test, like as I said before, is with a repeated measures design. It works just like an ANOVA. It calculates the F ratio by dividing the model mean squares by the residual mean squares. So essentially the F square is, not F square, the F is a ratio of systematic variation. So how much variation we can explain for our experiment or from the experiment divided by unsystematic variation, things that aren't explained by the model or by our experiment. Let's take that out. I don't know why that was there. But in all, so as far as assumptions for, man, I'm just not doing it today. And honestly, I just use this as from a different template, so that's why it's all there. So as far as assumptions go, it's essentially the same thing as in ANOVA. So normally distributed data, independence between observations. But the main difference is sphericity. And you can kind of say like it's similar to homogeneity of variance. So with sphericity, it's a general condition compared to compound symmetry. It's less restrictive than compound symmetry. Symmetry. There we go. So compound symmetry is where the variance for each condition of your experimental design are essentially like equal. And also the covariances between the pairs of conditions are equal as well. But with sphericity, it's less restrictive in that it's holding that the differences and the variances of each condition are roughly equal. So like if you were to like take each level and you at least determine the differences between like each pair of scores, these differences between the scores would have to essentially have to have equal variances. So yeah, that's pretty much it as far as assumptions go. So for this specific assignment, I've come up with the research topic of lighting and attractiveness. So essentially, I kind of wanted to see if lighting has a potential effect on attractiveness. But I will say this though, I'm not saying that lighting, uh, I'm not saying lighting, I'm not saying the conditions of lighting. So as far as dim lighting, a person will be rated as more attractive. I'm not saying it causes it. I'm saying it potentially influences it. So maybe I should be more specific. There we go. So the lighting conditions that I have are normal. So just like regular school lighting, bright, like really, really bright light, dim, kind of like if you were in a room with like one lamp light, that kind of dim. And then dark is kind of like club light, like club atmosphere dark. So not really much to see. Like if you have a strobe light and it's like just going, you can't really make out. Basically, what I'm saying is like there's little to no light with this case, with dark. So yeah, took a while to explain that. So the participants rated the attractiveness of the experimenter, given the lighting. This assignment uses the same participants for each condition. So like I said before, I'm trying to see if lighting has a potential influence on attractiveness. But the specific question that I kind of want to put out there to make it a little bit easier to see what I'm talking about: can lighting have a main effect on attractiveness? So my rationale for this test is that my predictor variable, lighting, is categorical. It has three or more levels. So it has 4 levels, so it's good. My outcome variable is continuous, and that's my outcome variable is attractiveness. So yeah, this I will do another video about, just so we can at least get all the results all together. And that's pretty much it.